Now it's fine. I do share screen. I hope it's going to work. Is it? Yes, it is. Okay, so today, as I said, we are going to finish the discussion about the Klein-Gordon and then Proctor equation, and then we'll move on to discuss Dirac and his equation. So just a quick recap on what we had. So we introduced the Klein-Gordon equation. Well, this is we started by discussing the Maxwell's equation and quantized them, and we found out the photon, and we looked at the different states of the photon and the polarization of the photon, and we saw that the polarization of the photon needs to be transverse. Okay, and the photon has a spin. And then we moved on to discuss a massive particle. That's a Klein-Gordon equation, describing a scalar massive particle. And the important thing is that it needs to obey the Einstein's relation, right? That E square is P square plus M square. And so for that, Klein-Gordon introduced the equation, D'Alembertian plus M squared of phi is equal to 0. Now, this is fully relativistic, right? So E is plus minus square root of P squared plus M squared. But the problem is that it has negative energy states. We cannot in quantum mechanics simply ignore them. And what even worse is that, it won't help me. What is even worse is that these states give rise to states with negative probability density. And in quantum mechanics, that means that the probability of finding a particle somewhere in space can be negative, and this is, of course, not physical situation. So on the one hand, this is relativistically correct equation, but gives rise to negative probability density, which is of course unphysical. And then I described the Feynman-Stuckelberg interpretation, which is still there until today, which basically states that rather than looking at the probability density as describing the probability of finding a particle, we look at it as the probability of finding the charge of a particle. And this, of course, can be negative because particles can have negative charge. And it kind of automatically aligns with the idea of antiparticles, etc. This is what we did about Klein-Gordon equation. Now, what I want to do, I want to slightly modify that and modify it by replacing the scalar particle, right? Phi is a scalar function, with some vector particle. So if we replace scalar with a vector, then rather than the Klein-Gordon equation, now D'Alembertian plus M squared, now it will be W mu is equal to 0. So this is an equation that describes a relativistic, vectorial, massive vectorial particle. This is known as the Proctor equation. It describes a relativistic vector particle. Now we know of two like that. These are the W and Z bosons. Well, actually 3, right? These are relativistic, massive vectorial particles. And remember that the role of these particles in the weak interaction is very similar to the role that the photon plays in the electromagnetic interaction. Also, for these particles, we have JPC, which we learned last time is 1 minus minus. And this is, of course, for exactly the same reasons as the ones that we have for the photon. I didn't ask you if you have questions about anything we said so far. So I should ask you that now. Do you have any questions? I want to say not too long. I will say a few about the Proca particle. So a few comments about it. Well, it's more than a comment, right? So a few things about the Proca particle. So one is about the Proca particle and the gauge freedom. So, basically, we can think of a Proca particle as a massive extension of the photon, right? So remember that we took the wave equation of the photon and we simply added a mass. But this is kind of a hand waving thing, because if you remember when we did the derivation of the wave equation for the photon, we had to apply the Lorentz condition, right, on the non-homogeneous Maxwell's equation. So basically what we did, right, we had the non-homogeneous Maxwell equation. And then we apply the Lorentz condition. Namely that d mu a mu is equal to 0. And that's how, and then we said we're in vacuum, so there's no current. And so we ended up with the wave equation for a photon. But when we add a mass term, then the basic question is, is it still allowed to do that? So can we still do that? If we add a mass term? So it turns out that the answer is yes. Of course, when we add a mass, then the gauge freedom disappears, but the Lorentz condition still holds. So I'm going to show it to you right now. So I'll just write it down. When adding a mass term, then we find out the gauge condition disappears. But Lorentz condition, gauge freedom, not gauge condition, but Lorentz condition holds. Gauge freedom. So what is the gauge freedom, right? That we can take the non-homogeneous Maxwell's equation, right? And we can change the potential. Right, a mu goes to a prime mu, which is a mu plus d mu lambda of some lambda. And the equation is not going to change. Now that's in fact what's going to happen, because I can simply plug it into the equation above, right? Less, right? So the Lambertian of a mu plus d, or a mu, plus d nu lambda minus d mu A mu plus d mu lambda is J nu, right? So in order for these two equations, for this equation to be the same as the equation here, then we just need that the D'Alembertian of d nu lambda minus d nu, and then we have d mu, which is just the D'Alembertian of lambda, is equal to 0. But since the derivatives are commutative, then this is indeed the case. Right? So if there are no sources, then the equation of motion without sources, the equation of motion of a photon of free. Right? It's just the Lambertian of A nu minus D nu d mu A mu is equal to 0. But now, if you want to add mass, basically we take the Lambertian and simply add the mass term. Then we end up that the equation of motion, Lambertian plus m A nu minus d nu d mu A mu is equal to 0. So this is not gauge invariant. Right? Because we get an extra term of m squared d mu lambda. Which we cannot cancel out. So we said that this mass term is what breaks the gauge symmetry. But as it turns out, the Lorentz condition still holds. This equation here still fulfills the Lorentz condition. So let's show that. But Lorentz condition still holds. Which the simplest way to take that is simply to take the derivative of this equation here, the one that I squared with the orange. So if I just take a d nu of this equation, then we have D'Alembertian plus m squared d nu A nu minus d nu d nu d mu A mu is equal to 0. Well, that's just D'Alembertian plus m squared d nu A nu minus D'Alembertian of d mu A mu, which is equal to 0. The two D'Alembertians cancel, of course, so we end up with m squared d nu A nu is equal to 0, which is just the Lorentz condition. We will discuss the importance of gauge symmetry and the break of gauge symmetry in the framework of the standard model, but that will be in a few weeks' time. The other thing I wanted to mention about this Procca equation is about the degrees of freedom. So remember that when we had a photon, we found that the photon has 2 degrees of freedom. These are the polarization, then they're both transverse to the direction of motion, right? What about the Proca particle? So again, we follow exactly the same path as we took when we derived the solution to the photon, to the quantized Maxwell's equations, right? So we search for free particle solution. So free particle solution should be of the form A nu is A epsilon nu E minus I P mu X mu. And of course, these are subject to the condition now that the particle is massive, right? So P squared have to be equal to M squared. Subject to just M squared. So, you know, the first side, it looks like there are 4 degrees of freedom, right? Because epsilon nu can take 4 values, right? But we have the Lorentz condition. So apply the Lorentz condition. Which we just saw it holds. Right, so I take the Fourier transform, so that would end up with the P nu epsilon nu is equal to 0, which of course reduces the number of degrees of freedom to only 3. So end up with the 3 degrees of freedoms. Degrees of freedom. Independent. Now, as opposed to the photon, right, we still had a degree of freedom we could play with, doing a little bit of math. Here we don't have this option because we cannot choose any gauge, right? So that means that a spin 1 boson that is described by a Proca equation can have 3 independent polarization states. That means that W and Z bosons have 3 independent polarization states. So, you know, if we have a spin 1 gauge boson that travels in the Z direction, the same as we did with the photon, we can repeat exactly the same arguments and the same calculations that we did when we derived it for the photon. And we find out that the 2 polarization states would be the circular ones. So we repeat the same calculation as for the photon. End up with 2 circular polarization states. Epsilon mu plus and minus. So minus will be 1 over square root of 2. That's a normalization. 0, 1 minus I and 0. And epsilon mu plus is minus 1 over square root of 2. 0, 1, I and 0. Identical to what we had with the photons. But now, in addition to these 2, we have a 3rd degree, which of course is subject to the Lorentz condition. Right, this condition here. So we have a 3rd longitudinal polarization state plus longitudinal polarization state. It's called epsilon longitudinal. And since it's subject to the Lorentz condition, if we have a particle that moves in the z direction, I can simply write it as 1 over m. That would be the normalization, pz 0, 0, and e. Of course, the normalization of 1 over m is just to ensure that when we go to the rest frame, then the longitudinal polarization in the rest frame is just 0, 0, 0, 1. Okay, so that's a small extension to what we did with the photon. Yeah, that's pretty much what I have to say about that. Any questions?
What does it mean for a particle to have polarization in the longitudinal polarization in the rest frame? What does it do or experience?
Well, it's an extra degree of freedom, right? When you say polarization, that means that you know, a particle can be the same particle, it can have different states, right? So it's simply, this is an allowed state of a particle to be in, right? You cannot have it for the photons, but you can have it if the particle is massive. Since it's massive, it does have a rest frame.
And so the field that it creates, or the field of the rest frame, would look differently?
You mean for the different states? For the, well, if it's a different field, that I need to think. I'm not sure I can answer you right away. You would think of a particle, the particle is an excitation of the field. If this is a different field, or it's different configuration of the same field, is something I need to think. I'm not sure I can answer to you right away. That I have to refresh my mind on these things. I'll try to come up with a proper answer by the next week.
Thanks.
Okay. Generally, I think it should be the same field, but I don't want to say something before I double check it. Any further questions or comments? Actually, pretty sure it is the same field because, you know, when you think of a photon, you don't say that you have different photon fields. You say you have one field. It's simply, no, I'm pretty sure actually it is one field, it's just a vectorial field. So if it's a vectorial field, you know, the same, just think of Maxwell's equation, right? It's the same electromagnetic field, it's the same electromagnetic potential. It can just have different orientations, right?
Yeah, but what's the orientation in the rest frame that's 0, 0, 0, 1?
That's what you mean? Okay, that I need to think a little bit some more, but what does it mean?
Or 1, 0, 0, 0, if it's the opposite, what?
1, 0, 0, 0 would just be, okay, it's a time x, y, z, right? So, okay, I'm not sure that I don't want to start giving you answers without thinking of them first carefully myself. Okay, I'll think and I'll come back to you with that on Tuesday. Fine. So now we're going to the next subject. It's a big subject, and it's a really cool subject, in my opinion. And that's called Dirac equation. Out of curiosity, how many of you have heard or have seen Dirac equation before? One, where have you seen that?
Advanced quantum mechanics.
Third year quantum mechanics?
No, advanced master's degree.
Master, that's fine. Yeah, okay. But this is not a master's course. This is a.
You asked me what I sold, so that's what I sold.
Oh, fine. Normally, you see that in a quantum field theory course. Really. That's normally when you encounter it if you don't see it here. Okay. So remember, Klein-Gordon. I told you they actually came even before Schrödinger. So I think it was 1925, and Schrödinger came in 1926. And it was a great relativistic equation. So Klein-Gordon. Psi is equal to 0. It's a great relativistic equation because it obeys the Einstein relation. E is plus minus square root of p squared plus m squared. But it has the negative probability density, which is pretty much problematic. Rho can be smaller than 0, so that's quite problematic. So we spoke about one solution, one suggestion how a solution in terms of interpretation, that this is interpreted in Feynman Stuckelberg's view as really describing antiparticles having positive energy. So Feynman Stuckelberg. That is antiparticles with positive energy. Okay, so basically particles move backward in time. Interesting. Now, when you think of it even more carefully, in the framework of quantum physics, the probability density doesn't even have to obey a continuity equation in the first place, right? Because particles can be created or destroyed, right? And so the probability of finding a particle somewhere, particle can disappear or can appear, right? Which is, of course, a phenomenon that does not exist in classical physics or in classical quantum mechanics. Well, can't really say classical quantum mechanics, non-relativistic quantum mechanics, but here it can. Right? So in relativistic quantum mechanics, particles can be created or destroyed, which means that or decay, right? So the probability density does not obey the continuity equation. Quantum field theory knows how to handle that. So Dirac searched for a solution. Basically, he searched for an alternative formulation of the quantum mechanics. And he did manage to find an equation which solves this problem of negative energies. But then it turned out that this equation also provides a very natural description of the spin of spin half particles, or spin half fermions. So essentially all the fermions obey Dirac equation. And because of that, nobody knows if it was planned or it just, one of these things that just come out of the math. You do the math and everything simply falls into place. So definitely one of the greatest successes of 20th century physics, this equation. Now today, it's understood, and I think it's studied in the framework of quantum field theory in a slightly different way than I'm going to introduce it to you, because it is introduced using various representations of groups, the Lorentz group, and sort of various bases of scalars and 4 vectors as well. But these representations give you various equations. You can find from the representations the Maxwell's equation, the Klein-Gordon, and the Dirac. But I'm not going to do it here. I'm just going to go the straight and simple way. I think this is the closest to the way Dirac himself found the solution. So it's I'm saving you all the high-level math that has been developed since then. So we said that the Klein-Gordon equation, so derivation and basic properties, derivation and basic properties. Remember that the Klein-Gordon equation, to get it, we started from the Einstein's relation, really. And then we promoted, remember I did this example using Schrodinger's equation, right? Then we promoted the energy and momentum into operators, which is what we do in quantum mechanics. That's how we got Klein-Gordon, right? The problem is that we have E squared and P squared, so we end up with a second order derivations, right? So Dirac was looking for a first order, right? That promote E and P into operators, and then obtain second derivatives. So Dirac was looking for a wave equation that would only be a first order in both space and time. In space and time derivative. So it must have some general form. Which we look something like E operator, right? Psi is alpha dot P plus beta M psi. Right now, sorry, so if we take the energy and momentum and promote them into operators, this will lead us to a first order derivations. I dt psi is minus I alpha j partial derivative with respect to j plus beta m psi. Now the summation here, j is only a space part, right? This is just a spatial part. J is just 1, 2, and 3. Right? Alpha and beta, these are constants. Alpha is a vector, right? Beta, these are constants. But these are not just numbers, as we're going to see shortly. And they don't necessarily have to commute with each other. That's an important point. Okay, now in addition, so Dirac proposed some sort of an equation, but it's a physics here. It's not just a game in mathematics. So he wanted this equation to describe a relativistic particle. But if it is to describe a relativistic particle, it must also obey the Klein-Gordon equation, because we know that the Klein-Gordon equation represents a relativistic particle, right? So it must, this equation has to satisfy Einstein relation. Right, E squared is P squared plus M squared. So how can we check if it is representing Einstein's equation, right? We can square it, right? So we can take the time derivative and note that it is alpha and beta are constants. So you know, space and time derivatives do commute. So I can take down you know, dt of all that, right? This is a wave function, so I can simply take dt times I, and I could simply, you know, square it. So I end up with getting minus dt squared of psi is minus I alpha j dj plus beta m minus I alpha k dk plus beta m psi. Right? That's a wave function. It's a new wave function that I have here. I take d over dt of that. This is just equal to that. So it's just equal. I just put down this equation again inside. Right? You all with me? Okay, since I don't want to get...
You're taking the square without absolute value. It's not the absolute value, right? It's a square.
No, I basically take... this is a wave function, right? This is all wave function.
Yeah.
So I just say I d over dt of that. What did I do?
So there's a minus sign on the left-hand side, right?
Yeah, I have a minus because there is an I times I, so it's
okay.
minus.
I looked like a bullet point. Okay, it's minus.
Minus. I squared, right? I times I. Let me write it down. Okay, I'm going to now multiply by -1 to avoid that, and let's simply expand. Expand. So dt squared of psi. Now I multiply by -1. I have minus, it's a -1, so I have what do I do here? Oh, that's okay. So I have alpha x. Now I'm going to do something which is completely illegal, and you know what I don't have? Well, alpha x. I just put the x down. It's completely illegal, but I'm doing it because I'm very lazy. Alpha x squared dx squared psi plus alpha y squared dy squared psi plus alpha z squared dz squared psi. Right? Minus beta squared m squared psi. That's the square terms. Now I have all the double terms, right? The mixed terms. So alpha x, alpha y plus alpha y, alpha x. D squared psi dx dy, right? Plus alpha y, alpha z plus alpha z, alpha y. D squared psi dy dz plus alpha x, alpha z plus alpha z, alpha x. D squared psi dx dz. Now I have the mixed term with the beta, so it will be plus I alpha x beta plus beta alpha x m square m dx psi plus I alpha y beta plus beta alpha y.
I think you're missing a few minus signs.
I don't think so, but let's check it in a second. Because I multiply by a minus.
Yes, but you only multiplied once on the right-hand side.
No, I multiply twice. You
multiply the left-hand side by one minus sign, but you have two minus signs on the right side.
No, minus I have. I and I cancel.
So then one beta m should be minus beta m, and at least the beta square term should have a minus sign.
Beta square term has a minus sign, that is true. I wrote it as a minus sign. Sorry if you cannot see it. Let me finish with that, and then you explain to me exactly what is wrong here. That's beta alpha z, d m d z psi. Now, where do you think I'm missing signs?
Now it'll be missing in mixed alpha beta terms.
Why?
Be
Have minus I alpha beta. I have a minus I alpha beta, but I multiply by a minus, right? Remember, I have a minus which I multiplied. So I guess that's going to be plus I alpha beta.
So on the left, you have I alpha minus beta times minus I alpha plus beta. So
have a minus I alpha
minus beta
times a minus
plus alpha plus beta, and then minus. Okay.
Agreed?
Yes.
Good. I'm happy. Anyone else have any comments on that? Here there is a minus right there. Yeah. Minus beta squared. Okay. So I want all that to reduce back to the Klein-Gordon equation, which I wrote down here somewhere. There it is. All right, this is the Klein-Gordon equation. But so the Klein-Gordon equation, again, this is d mu, right? So the Klein-Gordon equation is just dt squared psi is just dx squared psi plus dy squared psi plus dz squared psi plus, minus m squared. I move the m squared. So I can get that. So these two are equal. The equations are equal. If alpha and beta satisfy, or alpha j and beta satisfy a set of conditions. So one is that, of course, alpha x squared and alpha y squared, alpha z squared, and beta squared all needs to be equal to unity. Oh, what am I doing? Now I write it as an I because it's really a unity matrix. It's not just a number. We'll see that in a few minutes. And two, we need everything else to cancel out. So that means that we need that alpha j alpha k plus alpha k alpha j is equal to 0, provided that j is not equal to k. So they must obey anti-commuting relations. And the same with alpha j and beta. So the fact that they need to obey these anti-commutation relations mean that alphas and betas are not simple numbers. There are some objects that are constant, but they're not numbers, right? Now the simple mathematical objects that can describe, that can obey such commutation relations are matrices. So that means that the alphas and betas are going to be represented by matrices, but these are not any matrices. These matrices have to obey, or they have several properties. So alpha j and beta are represented by matrices. These matrices have several properties. You all with me so far? Are there any questions? Well, if you've seen it already, then I'm not surprised that you know what I'm talking about, but there are the ones who have not seen it. Do you have any questions? Some nice algebra, but let's look at the properties of these matrices. So properties of the matrices. So one, these matrices are traceless. These are traceless. Remember, trace of a matrix is the sum of elements on the diagonal. And in order to prove that, we're going to use the cyclic property of a trace. This is something which I hope that you've seen in your linear algebra course. Trace of A dot B dot C is equal to trace of B dot C dot A. If you haven't seen that, then consult your linear algebra, your favorite linear algebra textbook. We use I, and by I we know that beta squared is I. And we also know that alpha j beta is minus beta alpha j. So we can write down the trace of the matrix alpha j is equal to trace of the matrix alpha j times beta, right? Because trace of beta squared is the identity matrix. Using the cyclic rule, then this is trace of beta times alpha j times beta. And now I can use the fact that alpha j, the third part, which is alpha j beta, is minus beta alpha j. So this is minus trace of alpha j beta dot beta, which is just minus trace of alpha j. So these are traceless matrices. Right? The second property, is that clear to everybody? It's not very difficult. Some algebra. The second property is that the eigenvalues of these matrices are plus minus 1. So again, the proof is quite straightforward. So if V is an eigenvector, of alpha I with eigenvalue, right? ערכים עצמיים ומצבים עצמיים. Eigenvalue of lambda. That is that alpha I V is just lambda V, right? You all know that. Then I can multiply this equation by alpha I. Because the fact that alpha I squared is equal to 1, right? So alpha I squared V, right? Just alpha I right? It's just lambda alpha I V. Which is just lambda squared V. Which is just V. So lambda squared needs to be 1. Lambda is plus minus 1. Okay. Now, when you merge these two properties together, you arrive at another interesting property, which is that the dimension of these matrices, right, alpha I and beta, has to be even. Dimension of the matrices must be even. 2, 4, 6, etc. So proof is quite straightforward. We simply use the fact that the sum of eigenvalues of a matrix is equal to its trace. Right? Sum of eigenvalues of a matrix is equal to its trace. Right? And the eigenvalues we just know are just plus or minus 1. Right? So the only way the trace can be 0 is if the dimensions of alpha and beta matrices are even. Okay. The fourth property of the matrix, of all of the matrices, right? They're all Hermitian matrices. Why is that? Why is it? Why do I say these are Hermitian?
Because they're part of the operator E.
Exactly, right? Because I just look at the Dirac equation, right? They have to represent a real, a physical measurable quantity, right? A real wave function. So the Hamiltonian, Dirac Hamiltonian, as I define it, or Dirac define it, right? H Dirac alpha dot P plus beta M. This is Hermitian. Because we need to have real eigenvalues. So the alpha, J, and beta matrices must also be Hermitian. Alpha J dagger is equal to alpha J, and beta dagger is equal to beta. I'm not speaking gibberish, right? You all know what I'm talking about. When I speak of Hermitian matrices, yeah? Okay. So we have 4 properties of the matrices, alpha, J, and beta, each one individually, right? They are anti-commuting, they're traceless, and they have even dimension, right? Now it's really simple. In 2 dimensions, there are only 3 matrices that mutually anti-commute, traceless, obey all these properties. Right? In 2D, there are only 3 such matrices. Independent, only 3 independent, such independent. Now we can make many choices of 3 independent matrices, but the most natural choice will be the Pauli spin matrices. The most natural choice is Pauli spin matrices. So who have seen Pauli matrices? Raise your hands. 1, 2, 3. Okay, 4. Okay. Anyway, so sigma x 0, 1, 1, 0. Sigma y is 0, minus I, and 0. Sigma z is 1, 0, 0, minus 1. These are the Pauli sigma matrices. We will return to those. But we need 4 matrices. So it cannot be a 2 by 2 matrices. Okay. So the lowest dimensional object that can represent the alpha, j, and beta matrices are 4 by 4 matrices. And we can use higher dimension if we want to, there is no need. The lowest dimension object that can represent the alpha, j, and beta are 4 by 4 matrices. Which means, alpha, j are, they multiply the operators, right? The operator p. So that means that, these operators must act on a wave function, which by itself is composed of 4 separate components. Okay? So the operators by these matrices must act on a 4-component wave function. This has a name. This is known as the Dirac spinor. So psi, psi 1, psi 2, psi 3, psi 4. את יכולה לסגור את הדלת במקלחת? תסגרי את הדלת במקלחת בבקשה, אני טורקת. So, remember what we did. We need a quantum mechanical description of the wave function that satisfies the Dirac equation, right? So it has only first order space and time derivatives, right? And is consistent with Klein-Gordon equation, right? Which means it's consistent with Einstein's relation. So it's relativistic. And we found out that such a wave function does exist, but it must have 4 separate degrees of freedom. It's important. Just out of curiosity, do you guess what these 4 degrees of freedom would correspond to in real life?
The spatial coordinates in time?
No. These are 4 independent degrees of freedom of the wave function. Right? Each wave function, each solution to Dirac equation. In fact, for each Dirac equation, we have 4 separate solutions, 4 independent solutions for the same equation. Remember, equation corresponds to the mass. It has 1 mass right? One energy. This is a question to see if you got the physical insight. What would this correspond to? You're not supposed to know it now. We're going to derive it. Any clue?
Spin up and down particles and antiparticles?
Exactly. You see, it's all built in. That's what I told you. That's the magic. You end up with not a single particle. We have two particles, one with spin up, one with spin down. They have the same mass, the same energy. One will have a spin up and one spin down. And two antiparticles, they all built in into the formalism. Very cool, isn't it? Dirac was, you know, חיפש אתונות ומצא מלוכה. Was looking for one solution and he found four. Okay, so the conclusion is that to get a quantum mechanical QM, QM description of a wave function that satisfies the Dirac equation, first order space time derivative, and consistent with Klein-Gordon equation, relativistic. The wave function must have 4 degrees of freedom. Now, just as a comment, remember that if this is because you know, the particle is massive, so we had 3 alphas and 1 beta. Right? Now, if the particle was massless, right, then we had 1 less degree of freedom, right? So we just need 3 matrices. So we can have a representation using 2 by 2 matrices of a massless particle, right? Of course, the easiest way is to use the Pauli matrices, which we introduced. And this leads us to a 2-component object as opposed to the 4-component Dirac spinor. We have a 2-component object, and this is known as a Weyl spinor after Hermann Weyl. So just a comment for massless particles. One can find 2 by 2 representation. Often, you don't have to, right? But this is the most common one, using Pauli matrices. This is known as Weyl spinor. After Hermann Weyl.
Seth?
Yeah.
When you say consistent with Klein-Gordon, you mean consistent with relativity in general, right? Because Klein-Gordon is a scalar, and now you're using vector equations.
Yeah, I mean,
this does not reduce to the Klein-Gordon in any mathematical way, right?
Yeah, you're right. Sorry. What I want is to be consistent with relativity. I want it to obey Einstein's relation. E squared equals p squared plus squared. You're right that this is a bad phrasing. It doesn't have to be consistent with Klein-Gordon. It has to be consistent with the relativistic. Now, basically, we don't need to go further and specify which representation exactly we're going to use for the Dirac matrices. But we will do it because it's very convenient. We will have to use one if you want to do any calculation, right? So it's convenient to introduce the explicit form of alpha, j, and beta. There is more than one form, but the one that is used is the Dirac Pauli representation, a specific form or specific representation or conventional, specific conventional representate choice of representation of alpha, j, and beta is the Dirac Pauli representation. Which is based on the Pauli spin matrices. Well, I know it can be quite confusing if it's the first time you see that. Alpha and beta are objects. They can be represented. I can represent the same object in more than one way. I do what I do for convenience because I need to do some calculations at the end. Okay, and this is simply a convenient way. So the Dirac Pauli representation is that beta is just, it's a 4x4 matrix, right? So it's I, 0, 0, minus I. Don't get confused. And alpha I is 0, sigma I, 0. And I is a 2x2 identity matrix. Right, I is just 1, 0, 0, 1. So don't get confused by this compact notation. Right, it's a 4x4 matrix. That's as well. Right, so really, beta, right, is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Right. The same for the alphas. I just quick way of deriving it. Yeah. Writing it, not deriving it, just presenting it. So it's each block here, right? Each block here is a 2 matrix. Yeah? No, maybe? Okay, good. What about probability density? Remember that we started, Dirac main motivation was the negative probability density that we get in Klein-Gordon equation. So what about the probability density and the probability current density? So we are going to follow the same procedure that we did when we calculated the probability density for Klein-Gordon equation. Of course, now we have a wave function that is 4-component spinor, so we cannot simply take a complex conjugate, rather we have to take the Hermitian conjugate, right? So rather than complex conjugate psi star, we go to Hermitian conjugate psi dagger, which is just psi star. So Hermitian conjugate of the Dirac equation. I dt psi minus I alpha j dj psi plus beta m psi. This is the Dirac equation. Hermitian conjugate minus I dt psi dagger is plus I dj psi dagger alpha j dagger. Know that I switch the order. Plus m psi dagger beta dagger. These are matrices, right? Psi now has 4 components. So when I take the Hermitian conjugate, then I must switch the order. Right? You're all familiar with that from linear algebra. So I'm going to take the Dirac equation, right, multiplied by psi dagger from the left. Then I'm going to subtract this equation, which will be multiplied by psi from the right. And I'm going to use the fact that all the alpha, j, and beta matrices are Hermitian. Right? So we end up with I think did I do? No, nothing. So what did I do? Oh, nothing. Okay, I'm just switching the order, right? So I have here I minus, okay, so I dt psi dagger psi plus I psi dagger dt psi, that's the right hand, is equal to psi dagger minus I alpha j dj psi plus beta m psi minus plus I dj psi dagger alpha j dagger plus m psi dagger beta dagger. But beta dagger is just beta because it's Hermitian. And all for alpha j dagger I don't need because it's just alpha j. It's Hermitian. Psi. Okay. So if I now just divide by I, and okay, psi dagger m is just a number, so I have psi dagger beta psi, psi dagger beta psi with some minus. This cancel out. This goes out. Quite good, and I'm left with this. I need to move to the other side. The time derivative part. This will go on to the right. And the I I'm going to cancel by just multiply by minus I. And I'm left with nabla dot psi dagger alpha vector psi plus dt psi dagger psi is equal to 0. Cool. So if we compare that to the continuity equation, right? Compare to continuity equation. right? We can identify the probability density and the probability current density, right, of the Dirac spinor. Then we got the rho we can define as psi dagger psi. That's the probability density. And J as psi dagger alpha psi as the probability current density. Okay, are you all with me? Or have I lost half of you on the way? The problem is that there are a few people that speak, so I know what about you, but there are few people that do not really speak. So I don't really know what happened with you guys that do not really speak. Are you with me?
Yes.
Okay. Now we can write this as, in terms of, just expand it, right? So if we expand, rho, just psi dagger psi, this is just psi 1 squared plus psi 2 plus psi 3 squared plus psi 4 squared. Of course, this is always greater than 0. Problem solved. Right? Solutions to the Dirac equation always have non-negative probability density. So Dirac did manage to find a solution to the main theoretical problem of the Klein-Gordon equation. And the price is that the particles of Dirac has to be described by a 4-component wave function. But as I already told you, as remarkably, it turns out these components are not just 4 components, but they actually represent something which is real, right? The spin half, spin minus half, and a particle and antiparticle. Quite amazing. Yeah.
When Dirac came out with this equation, did they know about antiparticles, or was it just theoretical at the time?
No, it was theoretical. The first, it was in 1928. The first antiparticle was discovered by Anderson, I think it was 1932, a few years later. It was a prediction. It was an amazing prediction. And I think really, we'll talk about it. Dirac did not really know how to interpret this initially. There was this Dirac C, which has, it's a very nice visualization of what we're seeing here, but it's not true and it has several theoretical problems. But yeah, Dirac predicted antiparticles and they were seen 4 years after, and Dirac, of course, got the Nobel Prize immediately after that. Pretty amazing. They did know about the spin, right? The Stern-Gerlach experiment was done in the 20-something, I don't remember exactly when. So he did know that there are spin half particles. Okay. More questions? Okay, let's start discussing spin. I won't have time to finish today the discussion of spin, but I'll give you some feeling to, I don't know, keep you, how to say, curious about the spin of Dirac particles. Spin Dirac particles. Okay, so what I'm going to show now is that the Dirac equation describes spin 1/2 particles, right? In exactly the same way as the Maxwell's equation describes spin 1 particle, which we show, and the Klein-Gordon equation describes the spin 0 particle, scalar. Of course, spin 1/2 particles, we know these are fermions, so the Dirac equation is the right way to describe fermions. So in quantum mechanics, right, the time evolution of the expectation value observable, which corresponds to some operator O, was a long sentence, is what? The time evolution, or it's evolution in time, the time evolution of the expectation value. That's the correct phrasing, expectation value of an observable, right? Observable, something which we measure, right? That correspond to an operator O is d over dt O d over dt psi O psi. What is that? If you studied quantum mechanics, you should know. If you haven't, then you should know. It's very simple, right? I psi and what? What were written here? Nobody studied quantum mechanics. You studied, but you don't remember exactly. It's the commutation with the Hamiltonian, right? Am I telling you news? Is that news to you? Shouldn't be, right? Hopefully it's not. If guys, I'm very serious. I'm not sure, you know, when I this is the first time I'm delivering this course here in Bar Ilan, actually in general, and I prepare it aimed at undergraduate level, so it's not for masters. It's for master's level. Master level would be, then I would put some group theory. I do assume, I have to assume that you know some things about quantum mechanics, but not too much. If there is something which you do not know, feel free to ask. Feel free to even, you know, send me an email privately. I have been teaching quantum mechanics, so I have, and all my lecture notes are actually available online on my webpage, which is semi-ready. So feel free to go there and have a quick look at all these things. Okay, it's all there. So if there is something which you don't feel too comfortable with, don't be shy. Physics is not for shy people. I say to first years, no, everybody, nobody here is first year. But if there is something which you don't understand, then, you know, ask me. Worst case scenario, I won't know the answer, and I just say I don't know the answer, and I check it out. But that's my problem, not your problem. Okay, guys. So if we have an operator O that represents some observable, right, something which we can measure, right, that it commutes with the Hamiltonian, that means what? That the quantity that this operator describes is yeah, you're all muted. Yeah.
It's a measurable quantity and it doesn't interfere with the Hamiltonian.
Yeah, if it commutes with the Hamiltonian, what does it mean?
They can be measured simultaneously?
It's a constant of motion, right? That's what's written here. It's not changing in time. Right? It's a constant of motion, right? If you know, right, is equal to 0, then O, well, not O, right? The quantity, the observable associated with O is a constant of motion. Because its time the derivative is 0. Right? For example, right, the Hamiltonian of a free particle of a Schrodinger's equation, right, H Schrodinger is P squared over 2m. Forget about the V, the potential, right? Now this commutes with the angular momentum operator. Right? And that means that the angular momentum is a conserved quantity in quantum mechanics, the same way as it is conserved in classical mechanics. Right? Angular momentum is conserved in non-relativistic. If you're not sure why it is commute, go and check. They do commute. Now we have Hamiltonian of Dirac. Right now we are relativistic. So Dirac's Hamiltonian, H Dirac, is alpha dot P plus beta M. Now, what about, does this Hamiltonian commute with the angular momentum? Do this commute? R and P commute? Somebody?
Again?
I'm asking whether the angular momentum commutes with the Dirac Hamiltonian.
The mass term commutes.
Mass term, of course, will commute.
But the spin.
There's no spin here. I didn't say anything about spin. There is orbital angular momentum, R cross P. Let's look at the X, right? Alpha dot P, R cross P, X component. Alpha dot P, R dot Px will be Ry, so just Y, Pz minus Z, Py. So alpha dot P, Px would commute, so I don't care, right? So I have alpha Y, and then I have Py and Y, Py, Pz, right? Minus alpha Z, Pz, Py. Yeah, that's all we have, right? The rest would commute, right? Py would commute with Pz, Px would commute with Pz. I don't need to do anything, right? What is Py and Y? What is Y and Py?
The Py operator is the I derivative of Y.
Yeah, they don't commute, right? Y and Py don't commute, right? They're minus I. So we have a minus I alpha Y Pz minus I, so I have a minus alpha Z Py. So this is just minus I alpha cross P x. So in general, what do we have? We have that H Dirac on L is minus I alpha cross P. Just one small comment, right? H Dirac is a 4x4 matrix. This is a 4x4. This is R cross P, so I cross minus I nabla. So this is a number, right? But so in order to take it a 4x4 matrix, we have to multiply it by I. 4x4 identity matrix. So what did we get? About the orbital angular momentum, R cross P. Does it commute with the Dirac Hamiltonian?
Nope.
Nope, it is not. So what does it mean? What does it mean about the orbital angular momentum in Dirac theory?
That it's not a constant of motion?
It's not a constant of motion. It's a free particle, right? So L is not confirmed. But how can it be, right? But the particle is free. Didn't put any potential here to confine the particle. How can it be? So what? So in Dirac's theory, the angular momentum is not conserved. What did we do?
Is this why there's spin?
Yeah, very good. Very good insight. Excellent. What do we have to be conserved? The total angular momentum has to be conserved. J, right? J is L plus S, right? Right. Now, here is a very big difference between Schrödinger's treatment and Dirac's treatment. In Schrödinger, spin is completely separated from the orbital angular momentum. It lives in its own Hilbert space, right? They are completely decoupled. In Dirac, it is not. I haven't defined it. I won't define it now because we don't have time, but I'll find it next week, right? And the amazing thing is that indeed, in Dirac theory, the orbital angular momentum is not conserved by itself. But as we're going to show, the total angular momentum, orbital plus spin, this is conserved. So the separation in the framework of quantum field theory, that's another one of the things that quantum field theory is superior over standard quantum mechanics, non-relativistic quantum mechanics. You clearly see the connection between the spin and the angular momentum. They are not conserved separately, but they are conserved when they are together. Cool, isn't it? Very cool, but it takes time to make sure that you follow everything. Guys, I review some basics of angular momentum and especially basics of angular momentum in quantum mechanics, because we're going to use that in the next week. Okay, I think I also asked you that in the last problem set. I gave it, I think, as what to say. You don't have to do it. Just if you want to, just review. We got to the point that it's a good idea to review your knowledge of angular momentum and quantum mechanics in particular, because we're going to use it now. Chanukah Sameach, happy holiday. Any further questions? Any questions? No? Happy holiday to those who celebrate it. To those who don't celebrate it, have a great celebration and have a great weekend in general. And I'll see you on Tuesday. And please, really, I mean, we got to the point initially, you know, we were talking, there was more talking than technical points. And I think we've reached the point in the course that the things do get more technical. And I think you are encountering more and more new things that I believe many of you, I wouldn't say all of you, right? But many of you, likely this is the first time you're seeing them. If you have, you know, don't wait until the last week of the semester to come up with questions. You won't have time to study then. Everything will be messy. Do it now. You have time now. We're still very far from the examination period. If there are things which you're not feel very comfortable with, now is the time to review them. Come and ask, and I could guide you where to look for them. Okay.
תודה רבה, חג שמח.
חג שמח כולם.
חג שמח.
שבת שלום.
אסף,